The topic today is solving spatial problems using GIS or ArcGIS. The bigger picture thing here is spatial analysis, GIS analysis, analyzing your geographic information to find answers to problems, right, to better do your job. So this is where GIS, the software, the technology, the science, starts to be valuable in that it helps you to answer questions and solve problems and do your job better and save money. So there's a lot of things to accomplish when you're working with GIS, and this is one of the end goals, is to be able to solve problems using ArcGIS by means of spatial analysis or geographic analysis or GIS analysis. So spatial analysis is the process of using a map and GIS data to solve problems. So oftentimes we don't really need any advanced functionality or tools in the GIS to use the data to interpret patterns and things about geography around you that help you to answer questions. A lot of times you can just visually analyze a map to learn a lot about it. A good example of a map that I oftentimes just give a quick glance at to visually analyze, to try to make some decisions about where I'm going and how I'm going to get somewhere during the day, is Google Maps. Google Maps has a traffic layer. If you are not familiar with it, it's a very useful layer. It's here under traffic, and you can see if I turn it off, you'll see most of these lines are green. They turn off, and I can turn it back on, and you can see that's a traffic layer. It is from fast green to slow, which is the dark red. This data is streamed into Google servers through people's phones. So people's phones that have the Android operating system are relaying anonymous information back to Google to tell you where there's traffic. You can see here on Haywood Road, there's a little bit of slowdown, and there's some slowdown here on Patton Avenue. So I often, if I'm going out near the outlets and Bent Creek out here, going south of Asheville, there's this really congested intersection here where 26 and 40 and 240 all come together. There's been construction going on there for a long time. So if I'm driving out this direction from downtown, I will often turn on this layer just to give a quick look to see if it's really congested right there. And if it is, sometimes you'll see it backed up way towards town. If it is, I'll cut across 191 to get down there. In reality, usually 191 gets backed up too. But this is a layer that I quickly look at just to get an idea. Now, that's a visual analysis. To take the analysis further in what a GIS allows, if you put in your destination, like the Asheville outlets, and you ask Google to route you there, it will take into consideration the traffic, and at different times of day, it'll send you different ways based on traffic and other conditions. So that's using the GIS and an actual routing algorithm within the GIS to analyze the information further than you can visually analyze it, to give you information, an answer to your question, what's the quickest way to get somewhere. And so in the PowerPoint here, we'll look at some other examples of quick basic visualization and analyzing data by visually looking at it. This graphic on the left shows you the pirate attacks near the Horn of Africa between Somalia and Yemen. You can quickly see where they are concentrated, visually looking at the map without doing any kind of sophisticated analysis. This map is a before and after shaded relief map of Mount St. Helens, looking at before and after the eruption in the 80s. Is that when Mount St. Helens erupted? So you can visually see the impact the eruption had and the crater that was left and what the mountain looked like before. So visually, just interpreting information by looking at a map. Remember that we're spatial by nature as humans. We think about how we drive to get to school and to work every day. You're thinking about the shortest way or the route that takes you by the coffee shop or maybe the pretty drive. A lot of people cut through the Blue Ridge Parkway through town as a commute route because it's it's a nicer drive on the Blue Ridge Parkway. So we're doing basic geographic spatial analysis in our mind all the time. When you look at a map, you automatically are analyzing information. And the GIS lets us take it a step further to do more complex analysis that our brains might not be able to do. Whenever I look at this pirate attacks map, it often makes me think about a map of shipwrecks in the graveyard of the Atlantic, if you've ever seen them. And I did a couple of quick searches looking for some of this stuff before class, and I came up with this map. It's a National Geographic map, shipwrecks of the Outer Banks. I make it up to the southern Outer Banks pretty much every year, and I've always seen maps on the walls that show all the locations of the shipwrecks, and it's just an easy map to kind of visually analyze that there's a lot of something there. This is a good one. Now this map shows a tremendous amount of detailed information, but you can see there's a ton of shipwrecks. I did a little bit more searching and thought I'd just share some of this with you all because of the different ways you can search for data. Most weeks that pass in my life, I find myself searching for GIS data. This is a little bit off topic, but just to talk about searching for data, the search that resulted in finding this map was shipwrecks, Outer Banks, map. I also did a search for shipwrecks, Outer Banks, and shapefile. So when you're searching for data, take time to put in the file formats you think they might be out there, and that'll help narrow your search. This found a Google Maps map that showed some. I also put in shapefile, shipwrecks, Outer Banks, and KML. KML, Keyhole Markup Language, is the Google Earth format. That will often yield results, as well as GPX. GPX is a file format that comes off of people's phones. It's an open data format for GPS data, and so you'll find a lot of GPX files. As I looked, I realized that, and remembered, it's called the Graveyard of the Atlantic, actually, so I added that to my search. And Graveyard of the Atlantic and GIS came up with an ArcGIS online site that yields this. The ArcGIS online, remember, makes it pretty easy to share and integrate data with different people by sharing online. So I thought it worth, just because I was doing this search for these maps before class, making a little bit of mention of these search strings and modifying your search string as you find results or don't find results, and how finding some results may help you to modify your search string. Searching the internet is a very valuable skill in everyday life, and especially in something like GIS as well. Alright, so let's just move right along. So we apply a way of thinking that we call the geographic approach that helps us to think about problems and solve problems by integrating geographic information and computer software, GIS software, into the way that we approach problems. Okay, so the geographic approach is a way of thinking and problem solving that brings in GIS data and software and technologies into the way we look at, understand, manage the world around us. This geographic approach has a set of steps, and it's kind of a standard way of looking at any problem. And they're not really complex, they're pretty basic, but it's a good way to take a standard approach at any problem. And so this geographic approach, what is it? Well, the first thing you have to do is ask the geographic question. And you have to ask it in a way that the people you're working with or working for, that you're all on the same page. So when I taught at Greenville Tech, I had some students come in that were surveyors one day, and they said, Pete, we just got a job where we've been asked to identify all of the people who live within a half a mile of this chemical plant in Greenville. We also need to locate the people that are within 1 mile and the people that are within 1.5 miles of a chemical plant. I said, okay, well, why do you need to know that? They said, well, the chemical plant polluted the area around it, and the people within these search radiuses are going to get paid out because there's been higher rates of cancer incidence. This is a true story in Greenville. I can't remember the name of the company or the plan or the details. It's been a decade at this point. But the students wanted to know who lived within a half a mile, and a mile and a half. The people that lived really close were going to get a bigger payout. So that's the question. How close do people live? How many people live within these search radiuses? So from there, you have to acquire the data. This particular example, there were not a ton of data sources that we needed to acquire. We needed the plant location. We needed a point for where that plant was. We needed some parcel data that showed who lived around the plant, so we could tell the ones within each radius. We needed maybe some streets data and some other base data, might be nice to have, but not a ton of information. So from there, we make sure that the geographic data suits our purposes. Things like the parcel layer. Does the parcel layer support what we want? The parcel layer, in order for it to support what we needed the parcel layer to show the owner name and their address. And so you need to look at your layer and make sure it's got the types of attributes you need and the spatial geometry that you need. You need to inventory your data. Check it out. Make sure it supports what you want. From there, you analyze the geographic information. So part of the analysis in this project was to generate some buffers around the plant. So with the buffer tool, you can generate concentric circular buffers around points at a half a mile, 1 mile, and 1.5 mile. That generates a new layer with polygons in it. Using those polygons, you could select the parcels that fall within each polygon using a select by location. So we had to process some data and generate some new data using a buffer analysis. And then we had to select the parcels that fell within each one of those buffers. And after that, we had the selected parcels. We could export the tabular information, owner and address, to an Excel file. And we could do a mail merge in Microsoft Word to mail all these people a letter. In that case, that was acting on what you learned. Okay? In this case, they didn't even send out maps or anything. The result was this spreadsheet of addresses. So, you know, a GIS is not always about the map. It's about analyzing information oftentimes, though. So that's a pretty simple example, but if you follow these steps, you kind of have a standard way of approaching it. And sometimes you might get to one step and realize you have to reframe your question. Maybe the data doesn't support what you're looking at. Maybe you need to find a different way to approach the problem. So this is all spatial analysis. Spatial analysis is the systematic extraction, creation, or modification of spatial data to address a question or solve a problem. So it's taking data, working with data, processing the data, updating the data, modifying the data, doing things to the data in a way that allows us to better understand the world around us. The benefits of performing analysis are things like getting answers to questions. Performing analysis will help you get an answer to a question. Solving some kind of spatial problem. Gaining a better understanding of the world, making more informed decisions, and saving money. Now, answering questions, you do get an answer when you perform analysis, but it's not always going to be the right answer. Not only is this a geographic approach, it's a scientific approach. And this is like the scientific method where you have a hypothesis, you test the hypothesis, you find answers, and then you go retest it. Okay, so just because you get an answer doesn't mean that it's the best answer or the only answer. You need to have a critical approach to looking at your results and determining if it's what you thought it would be, or maybe if there's a different way to approach the problem that gives you different results. The last two bullets are definitely worth a mention: the making more informed decisions and saving money. At the end of the day, all the stuff we do with GIS, these are the things it should be helping with. If it's not helping you make a better decision and probably saving money as well, then you're not really getting a return on your investment for the software and the data and the expertise it takes to have a GIS. That's really what it's all about at the end of the day. We have to do a lot of stuff that you just get bogged down in the details of keeping the data up to date and storing the data and doing all these different things. But at the end of the day, you want good data that supports analysis to help you make better informed decisions. So how about some examples? Here is a very easy example. What is the nearest feature? That's a common thing we ask with the GIS. In Google Maps, the fastest route or the closest is easy to determine, but also just visually looking at a map. So here are some campsites. You can, if there's a trailhead on here, you might decide you want to go to the closest campsite instead of the furthest campsite. This is the kind of thing that we do all the time. You probably have a favorite swimming hole or fishing spot. You probably have a couple of them. And in one afternoon, if you've only got a little bit of time, you probably choose to go to the closer one than the one farther away. So the GIS can answer these questions very quickly and very precisely. Here is an example of how things change over time. So another example of spatial analysis is looking at trends of change over time. This example shows proportional symbols to represent population levels in California for each decade between 1900 and 2000. In this case, you can see how population center has not only grown, but it's also shifted south through California. So this is a great visual way to present the results of analyzing information by symbolizing and showing spatial location on a map. This is a really good graphic that helps people to understand data and information. So looking at change over time is a good spatial analysis tool. Also looking at spatial patterns. Spatial analysis can help us to determine spatial patterns in data. In this example, we look at the average mortality rates in the Midwestern United States. The red areas indicate higher mortality rates, and the blue areas are lower mortality rates for a specified age group of the population. This type of analysis is very useful and very common in the GIS field. Someone I know here in town has a master's in public health from Chapel Hill, and they also focused heavily on GIS in their public health graduate work. They look at things like per capita spending on health care and compare it to the types of care people get, compare it to population as well as income, and the kind of outcomes people get from their health care. So it's pretty neat the kind of analyses this person looks at using GIS in the healthcare field. So he provides a lot of insights to healthcare providers and lawmakers and hospitals on what kind of results people are getting for the amount of money spent and the kind of care they're getting in different areas. It's very interesting to look at the metrics that he uses for these kind of analyses. Site selection is another good example of a common type of spatial analysis. So the question is, what is the best location for something? To choose the most suitable location for something, such as a store or a wildlife habitat, you have a criteria that pinpoints why one location would be better than the next, based on specific needs or requirements. So I recently did a bunch of site selection work for a solar company that builds solar farms. And this company came to me and they said, we'd like for you to look at all of the parcels of land in a county. The parcels are polygons. And we want you to take out of each parcel, we want you to subtract out of that piece of land the wetlands, because they can't build in a wetland, the floodplain, because it starts to get into hard permitting stuff similar to wetlands, take out anything over 8% slope, because they don't want to grade a bunch. Also, take out the forested areas. To deforest a piece of land to put in solar is very expensive. So essentially they're looking for flat, open land, not forested, no wetlands, no floodplain, and it needs to be within 1.5 miles of a substation of the power company. So that's a site analysis I did on a county-wide level and came up with hundreds of potential parcels that they then contacted the owners and pitched to them the idea of putting a solar farm on their site. They needed 25 acres to build one big enough to make it worth doing. So that's an example of site selection that I recently, it's been a couple years now, but pretty recently I did. In the training, there's a wildlife habitat example where they're looking for wildlife habitat that's close to water but away from roads, and it needs to be in a certain kind of tree cover and forest type. We've talked about analysis a little bit without even knowing we were talking about spatial analysis. Last class we talked about queries. We talked about attribute queries and we talked about location queries. This is kind of the jumping off point for analysis. Doing an attribute query is a really basic type of analysis. You can do a query in the North Carolina counties layer for all of the counties with a population greater than 100,000. And that's going to result in a selected set of features of all of the counties greater than 100,000. That's asking a question of the data and getting an answer. So just performing an attribute query or a spatial query or select by location query, it's performing analysis. Granted, it's reasonably basic, rudimentary type analysis, but it doesn't mean it doesn't provide very useful information. And it's more common than doing really complex analyses. Some other common geoprocessing techniques, and I'm going to demonstrate a bunch of these as we get into them. So when we work with our data, we often geoprocess it. So geoprocessing is a term you hear used in conjunction with analysis often. Throughout an analysis project, we oftentimes geoprocess our data, processing our geographic data. So one of the things that we do is that we extract data. There is a geoprocessing tool called CLIP that allows us to do this. Okay, so for instance, let me just jump right in and do a demo. So for instance, when you do a GIS project, you always have an area of interest or study area, the area that you're mapping. In this case, let's just say we're making a map of Bent Creek. So I was provided the boundary of Bent Creek there in a red outline. You can see the roads of Bent Creek. There are these black lines, and then there's the streams. Now notice my Bent Creek boundary and my roads are all just Bent Creek. They don't extend beyond the boundary of Bent Creek. But I have a streams layer that extends beyond Bent Creek. This is really common. You come up with a study area, you have an area you're mapping, but you have some data that extends beyond the area. You need to select it down to or clip it out using a clip tool. Now last class in the select by attributes and select by location, we said how when you select features, one of the common things we do is we export them to a new data set. That results in a similar outcome as what this does. I could select by location and I could select the features from that streams layer that intersects that boundary, and if I click apply, notice what it does. It selects any streams that touch that boundary. I could export those streams to a layer called Bent Creek. But since these streams, some of them extend beyond the boundary, in this case I want just the streams. I want them to be just within that boundary. So what a clip does is it does a cookie cutter operation, and it cuts out based on the polygon or polygons in the clip layer. So let's just look at this. Now, geoprocessing tools are in ARC Toolbox. The really common ones are under this geoprocessing dropdown. So we'll talk about most of these today because they're the really common ones. You can go to ARC Toolbox to see them all. The geoprocessing tools are one of the places that you'll see a difference in the license levels of ArcGIS. The higher license levels have a whole lot more tools for interacting with your data. So let's look at CLIP. So geoprocessing operations. This operation takes an input file. That is what is going to be clipped. You have to tell it what to clip by, and you have to give it an output feature class that gets created. Geoprocessing does not modify the original data. It outputs a new data set. That's key to the definition of geoprocessing. It applies an operation to some data set and outputs a new data set. So the input features, we want to clip the streams. We want to clip by this BC boundary. And it's going to put this output in this default geodatabase in my ArcGIS folder. I could output it to a shapefile or to other places. For the purposes of this demo, it'll be easier just to let it go there and not even change where it's going. I'll click OK. You'll see it's saying it's clipping down here. And when it finishes, you'll see this thing come up with a little checkbox saying the clip worked. And there's a new layer here. Now I need to clear my selection. And let's turn off this streams layer. And you'll see that it's the streams just inside of Bent Creek now. So that's the clip operation. Again, it's a pretty common thing that we do. If we go to the geoprocessing clip, I should have clicked on this show help to show you how this gives a nice little graphic for what happens when it gets clipped. And so all the tools have this nice little help area here that you can use. All right, so that's a clip. How about proximity analysis? Proximity analysis is another really common thing we do. The most common type of proximity analysis is a buffer. A buffer is a geoprocessing operation that uses proximal relationships that are important to a spatial problem. So the buffer allows us to create a buffer based on a distance around a feature, and it outputs a new feature class with those buffers in it. To actually create the buffers are pretty nice because buffers on a map are a really nice visual cue to someone reading and interpreting a map. We can do a select by location and select features within a distance that uses a buffer without actually showing you the generated polygon. So select by location does a similar kind of thing, or you can get similar results by selecting by location if you do within a distance of. But the actual buffer geoprocessing tool provides actual geometries that give good visual cues on a map, and also we could do other things with those, like clip or intersect or other things. So let's give a quick look here at some buffers. So these are the schools in Buncombe County, and I tried to find some registered sex offender data that I could download and put in here to buffer the schools and compare to that, but I couldn't get any downloaded for Buncombe County quickly and easily. But just an example that you might be looking for distances from a school to something like that. One of the very first spatial analyses I ever did when I was working for a county in South Carolina. I was actually finishing graduate school. I hadn't even finished yet, and there was a new a permit had been submitted to the county for someone to open a gentleman's club in the county, and they wanted me to buffer that location and then put all the churches on the map to try to find if there was a church within a certain distance of this location, because there was a law that said there couldn't be. And so that was a basic analysis I was doing. I also did some other work very similar to that with alcohol sales in South Carolina and their proximity to churches because of a bunch of laws called the Blue Laws. But that was some real common kind of basic proximity analyses that I perform. But so what I want to show you here is how the buffer tool works. So I'm going to go geoprocessing and go to buffer. The input features, I'll pick schools. It's going to output a schools buffer file that'll be a polygon feature class. I tell it the linear distance. Let's say, I don't know, let's say a half a mile. I don't know why. I don't really have a good reason for the distance there. But a few things that I want to show you here. When you create a buffer, you can decide whether or not the overlapping buffers, they dissolve out in between them. Usually, you tell it to dissolve all here, and that will dissolve overlapping buffers. There are times when you don't want to dissolve them all. In graduate school, again, I knew someone studying red cockaded woodpeckers, and they are an endangered species. And if you can imagine, these points on this map were the tree locations for nest for those red cockaded woodpeckers. They were trying to determine the foraging area that they needed to forage for food and shelter and that kind of thing. So they know that red cockaded woodpeckers will not compete for foraging area. And so when the trees were close together and there was an overlapping buffer, that area of the overlapping buffer was really important because the birds would not encroach on each other's area. They wouldn't compete. So they wanted to keep those areas. I tell you this because it's good to know it's the default to not dissolve, but I want to make the point that most oftentimes we do dissolve. In this case, I'm not going to dissolve just so we can see what they look like overlapping. Buffering. Okay, there are my buffers. Okay, it's a new layer. And you can see how they're overlapping there. Okay, what if I do that same buffer, but I let them, this time I'm going to dissolve. Schools, school buffer is going to put a 1 on the end. Don't worry about the ActiveX controls. And this time I'm going to dissolve all. Now there's a lot of other settings in here that we'll talk about, but let's just watch this, what happens. Okay, so that didn't work at all. Not sure what happened there. What did I do? It was in feet. Thank you. So I did 0.5 feet on that buffer. Thank you. If we turn the schools off, can't even see it at all. Let's just try that again. Geoprocessing buffer, schools, buffer 2. Yes, 0.5. I didn't change that, did I? Miles, and let's dissolve all. There they are. Okay, so these, if we symbolize them a little bit differently, you'll see that they dissolve the lines and the buffers. Okay, so dissolve or not dissolve overlapping buffers are something that you should consider. Now, I say this because it's important, but there's one example where I see people not dissolve often, and you should. When you are buffering line features, like roads, I see people oftentimes, see how these streams are made up of a bunch of different line segments. And so when you buffer streams, if you don't dissolve, it makes a whole bunch of little buffers along it, and you definitely don't want it in that case. So let's buffer this major streams layer, and I'm just going to let it keep dumping into the that default geodatabase. We'll do 500 feet, and I'm not going to dissolve type none, and let's see what it does. Okay, so you see how these buffers, or there's all these individual buffers because there's individual line segments. And that's how most streams layers are built, as well as roads layers. They have individual line segments that'll get all these individual buffers. So if we dissolve those, you'll see it gives a much better look. And I will buffer all, or dissolve all, apologies. And as it runs, there, it looks more like that. Okay, so that looks like a better stream buffer there. So dissolving versus not dissolving overlapping polygons. With points, there's often the question you really kind of got to figure out what's best. With lines, you usually want to dissolve. You can also do multi-ring buffers. I could do a buffer every 500 feet to get multiple rings. I can buffer lines, points, or polygons. I can buffer insides of polygons by using a negative number. So if you wanted to create like a no-wake zone on the inside of a lake, you could buffer the inside of a polygon. You can also buffer based on an attribute. So I don't have a great example for this right here, but I can just kind of tell you one as we look at this points layer. Let's just imagine that this points layer had 3 points in it. These 3 points. And this layer showed radio towers. And in the attribute field for the radio towers, there was a watts field that had how many watts each radio tower put out. Instead of giving it a distance, 500 feet or half mile, you can, in the buffer tool, you can tell the buffer tool to get the information from a field that has different numbers in it. So the buffers would be different sizes based on the attribute information. So if you got an attribute field that has different numbers in it for some kind of measurement, you can point to that field, and each point, polygon or line, will get a different size buffer based on the information in that. So you can do a lot with buffers, and like I said, they're nice visual cues and things to have on maps. They're nice to look at. Okay, I think I covered most of that slide. Covered most of this. All right, so on to overlay analyses. Overlay analysis operations allow you to combine data from multiple inputs into one layer that allows for easier analysis. Okay, so what it does is it smashes 2 layers together. So if you had a parcel layer that showed all the parcels in Buncombe County, and then you had a land use layer or a zoning layer, you could smash those 2 together, and where they intersect, it combines the attributes and the geometries. So intersect can be used on any feature type. Union is used on polygons. If you look at the overlay operations in Arc Toolbox, it's one of the places you'll see a difference in license levels. The advanced version of ArcGIS has this many, 7 overlay operations. If you have a basic license, all you get is intersect, spatial join, and union. You get these other types of overlay operations with a higher license level. It is worth a mention that that free GIS software that I've mentioned called QGIS, you can search it and find it. It's a free open source GIS software. It is incredibly powerful, and you can do any of these overlay operations in it. So if I'm ever using a basic license level of ArcGIS and I need one of these tools, I dump the data to a shapefile and I do it in QGIS because it's free and it's powerful. So let's just look at intersect. What does intersect do? Well, let's just look at the help. It computes the geometric intersection of the input features, and in the output it only retains the areas in common to both. So this area is in common to both, and so if this was someone's piece of land and this was a different layer of zoning and this was commercial and this was residential, it would create this new output, and this would also have the zoning type assigned to the parcel. So let's look at an example of this and see if I can demonstrate this. So this is some land use data for North Carolina, downloaded from the US GIS site. Okay, and here's the parcels for Buncombe County. If I zoom to this parcel layer, there's Buncombe County parcels, and there's the land use type under it. Okay, so if you click on this right here, you'll see that is deciduous forest land. And this blue is residential. So if we overlay the parcels on it, and I'm going to make these things hollow so I can see them, no color, maybe a yellow outline, we'll be able to see that. Yeah. And we're going to zoom in to a couple of these areas just to kind of understand what it's going to do before we run the tool. All right, there it is. So this parcel right here, that parcel will be split into two parcels. It will retain all this information, but what will be added will be the information, the tabular information from the land use layer below. So it's going to have cropland, pasture as part, and residential as the other part. That's not sure. Oh yeah, cropland, pasture, and deciduous forest land. Okay, so let's just run this operation and see what it does. Now, some of the big differences in all these overlay operations, well, I mean, if your boss came to you and said, I want to know the land use type for all the parcels in the county, once you smash them together like this, you could run some statistics on it and tell them really easily. So let's look at this layer. So notice that the land use data extends beyond the county. If you do an intersect, that particular overlay operation, it will also clip the data out to this county layer. So an intersect operation only retains the area in common to both. If you did a union, another type of overlay operation, it would retain all the features from all the layers that it get input. These polygons would be retained, but they wouldn't have owner information for them. They just wouldn't, because there's none to intersect with it. So the difference in a lot of these overlay operations are what gets retained in the output layer. So an intersect is a lot like a clip. It's going to kind of clip this area down to this yellow layer, the parcel layer. The big difference is a clip doesn't combine attributes from the two layers being used. The intersect, the overlay operation, it clips the data down, but it also combines all the information together. So let's look and see what happens when we intersect this stuff. We want to intersect the parcels with the land use all, and we're going to let it dump out to parcels, land use, intersect. Join the attributes. There's some other things there's some other settings that we're just going to roll with. And you can see it's intersecting. Hopefully we'll see a little green checkbox come up in just a sec. Now these are a couple of decent sized layers with a lot of polygons. I can't remember how many polygons there are in the parcel layer, like 150,000 or something like that. So there's a decent amount of information here. I used a process really similar to this in grad school when I had points of tree locations across an entire national forest, and they told me they wanted me to tell them what soil type each tree was on. So I combine the attributes from a soil layer to the point that it fell within. That did a very similar thing. These days we do that with what's called a spatial join. So you see the checkbox and the intersect seem to work. If we zoom into it here, all right, let's see. Let's look back at this. Let's get zoomed to, okay. So you can see this area right here where if I turn off the land use, it's hard to see that. Let's make this all red. All right, so there's my parcel layer. Here's the land use under it. So these parcels should be split into multiple parcels. There, that show this parcel right here. It's now made of 2 polygons, but if I identify it, I get this person's name and everything. But if you go on down, you'll see the land use. So it's a pretty good way to combine information then by overlapping and overlaying these layers. All right, so those are overlay operations. Again, they allow us to combine information to perform analysis. And you can do it on large data sets for lots of information. In the example here, the intersect is very similar. They are intersecting a land use layer with a buildings layer. The intersect means that only the buildings are left, but each building has that zoning information attached to it. I mentioned the clip versus the intersect thing. Essentially, clipping is just a cookie cutter operation that does not combine any attributes. The only attributes left are the ones that were in the original layer that was clipped down. Intersect retains only the areas in common to the two, so it can perform a clip operation while combining the geometries and the attributes. So we've been talking about geoprocessing and analysis. What's the difference? There's no clear distinction between what is processing your data versus what is analyzing your data. Geoprocessing and analysis work hand in hand during any GIS project. We use geoprocessing tools to process our data. You could argue that a clip operation isn't really analyzing the data, it's just processing it to make it smaller. You could maybe argue that a buffer is more of an analysis, but you know, it's more what you do with the buffer that provides the analysis. They work hand in hand. Don't get caught up in if one's processing versus analysis. They work together to get to the end point. Okay. So how about sharing the results of your analysis? Your results are no good if you can't give them to people. So one of the ways we share our results are by exporting a map to something like a PDF or a JPEG to provide to someone. We're often performing analysis and making maps for people who are not GIS users who do not have ArcGIS. So you provide the information to them in a way they can open it and view it. A PDF map or a JPEG exported is a good way to do that. We oftentimes also provide information in just tabular format. The example of all the people living within a half mile, a mile, and a mile and a half of that plant, literally that was the deliverable, a spreadsheet that showed that. You want to document your process so you can justify how you did it and why you got the results you did. But you might not give a map to someone. Maybe you just give them a spreadsheet of addresses. Some newer ways to share information are layer packages and map packages. If you're sharing the data with another GIS user, we can share layer packages, which I'll demonstrate here quickly. So what a layer package is a way to combine some data with symbology. So here's a land use layer, and I've taken some time to symbolize it with these colors. Now, most of the times people have a nice standard way of symbolizing things, and they want people to make maps using those same standard symbols. A zoning map for the county is a really good example. The zoning map at the county has a standard set of colors for how they color different zoning types. There's shades of red for commercial, shades of green for public spaces, things like that. And so when the county, when someone requests the zoning layer to make a map for their own purposes, the county likes to give them the symbology as well. Because remember, when you store data in a database, here is some land cover data that I'm looking at here, and if I load this land use all, it's a shapefile here. If I load it into ArcMap, it comes, everything symbolized the same symbol. That's the default operation in ArcGIS. The symbology is not saved with the data in the shapefile or the geodatabase feature class. That symbology that we spent time symbolizing here is saved in the map. And so when you give someone this shapefile, they don't get this symbology. What you can do is you can save as a layer file. What that does is it makes a .lyr file, and if you share this LYR file and the shape file that goes with it through a layer package, you can share the symbology as well. I'll call you right back, sorry. I meant to send her a text. Alright, so you can combine this symbology with a layer file and the data in a layer package. Alright, so layer packages are nice. The other way of sharing a full map package. So if you have a full map with a bunch of data, symbolized, labels, everything, you can share a map package. What a map package does is it combines the map and all of the data into one file put together, and then it extracts it back out on someone else's system. I have someone helping me on a map right now, and I've got tons of hours in on this map. It's symbolized and labeled, and it's probably got 50 layers in it. And for him to help me with what I need him to help me with, I need to give him that whole thing. So I'm going to create a map package and give it to him. He'll extract it onto his system, and then he can work with it. The one thing about map packages, when you extract it to your system, it puts it in kind of a weird location. It puts it in the ArcGIS folder under some really cryptically named folders. So just beware where that thing gets extracted to and pay attention to it. The big thing is to remember that map documents, this demo.mxd, is no good without the data that it references. And so if I give someone this MXD, they can open it, but they won't see this data that's here on my servers. If I make a map package, it's going to take that data off the server and everywhere else data is, and it's going to put it with the map document and put it on their system. So map package is another good way to share data. Alright, so this analytical process, the scientific process we go to, this is some kind of bigger picture stuff. Let's talk about it a little bit, and this is related to the geographic way of looking at things. You have to define a problem, define the criteria that allows you to measure your problem, identify data that will help you to look at the criteria and help with your problem. Sometimes you realize that there's no data available, or maybe you can't afford to build the data or collect the data or buy the data. So you have to go back and redefine your problem. It's an iterative, cyclical kind of process. Even when you get down to the next level and you're planning your analysis and preparing your data, maybe you find more insights during that part of the process. So you might loop back up and replan what you're doing. Eventually you execute your analysis and you examine and present the results. And maybe you're happy with the results, or maybe you're not. Maybe you go back and you redefine the problem again and start over again. Okay? So, getting a little bit more specific, defining the problem. An example, what parts of the beach are most likely to suffer damage in a hurricane? Maybe you break it into smaller questions and you say, well, let's just look at the populated areas of the beach. Let's not worry about the national seashore up there where there are no houses. You know, coming up with what exactly you're looking at. Define the criteria. What defines damage? Are we looking at erosion? Are we looking at property damage? If we're looking at erosion, are we talking about 2 inches of erosion or 2 feet of erosion? You have to define the criteria that helps you to evaluate what you're looking at. Identify the data. Is there data? Do you have to collect it? Do you have to buy it? And do you know that much about what you're looking at? Oftentimes, as a GIS person, you're not the domain expert. You're working with someone who's an expert in soil and beach erosion and storms, and you're the GIS guy working together with someone. Sometimes you are the domain expert, but oftentimes you're not. I've worked in school district planning, I've worked in county planning, I've worked in public works, I've worked with tax assessors. My real domain expertise is forestry, forest recreation, forest ecology. So as a GIS person, you find yourself working in a lot of different domains, and you rely on people in those domains. Planning and preparing, make sure to plan. It helps prevent mistakes, which saves time. Oftentimes, you realize more data is needed. There's back and forth between the planning and identifying stage, and a lot of times you test a particular approach to make sure it accomplishes your needs and make sure you can understand how to use it. So you do a little pilot test project. When I was doing that solar site selection stuff, I ended up doing that 3 or 4 different ways, getting slightly different results in the different orders that I extracted out different parts, and the different ways I did it. I was getting some different results, and it took a while to refine my process. When you do plan, an analysis diagram is often useful. An analysis or workflow diagram should identify the sequence of steps you take, the specific tools you're going to use, and the data required and the data produced by each tool. So in this case, if we consider Victoria Road here on our campus, for example, Victoria Road is the only way in and out of this campus. It's a 2-lane road, and when class is let out or when school is canceled for inclement weather, it takes a long time to get off campus. Also, if you leave campus when Asheville High is getting out up there, it takes a long time to get off campus. So we've been asked to look several times at alternate routes to get off campus and off Victoria Road. So one of the things they've looked at is widening Victoria Road. So if we wanted to look at widening Victoria Road, we'd need to contact all the people who live on Victoria Road. So how would we do that? Well, we need a streets layer, but we don't need all the streets. We just need to select out Victoria Road. So we take all the streets and we select out Victoria Road. From there, if we buffered Victoria Road, whatever distance we needed to widen it, say 40 feet, 20 feet, whatever it is, you could then overlay that buffer with the property owners on the sides of the road so that you could select the property owners based on the ones that touch that buffer. You could also do a select by location without even creating that buffer and select the parcels within a distance. The buffer's nice because it gives you that nice visual cue. It's also nice in this case because where it overlaps the adjacent parcels to the road, if you did an intersect or a clip, in this case both would work, you could clip out the parts of the parcels that extend, that buffer extends over, and you could determine how much property they would lose by clipping out that part of their parcel. You could look at a percentage of their total parcel. So having that buffer is a nice visual cue, but it's also a polygon that you could use to clip and further pare down the data and analyze it. From there, you could send out a letter to the parcel owners. Same kind of thing that we talked about before. Preparing your data. Data rarely comes exactly as you need for the analysis. You might need to add or populate a field, update features, correct data errors, change coordinate systems, clip, merge, dissolve, all of those things. I got a trails layer for Ridgecrest. I was working on a map for Ridgecrest. They gave me a trails layer. That trails layer did not have the trail names in it. It was just the lines. I had to add a name field and go through and select the 8 trails and give them names so I could label based on those names. Then I could use the labeling field. So that's a real easy basic update. Sometimes the updates are big and take a lot of time, but you just have to do those things. Another good example is the streams layer for Bent Creek that we had to clip down. You're constantly doing that kind of thing, trying to get our data in the right shape, size, format, area, extent, coordinate system, down to what we need. When you plan thoroughly, the analysis is usually pretty straightforward. You simply follow the steps in your diagram. It's not a terrible practice to work on a copy of your data. If you use some kind of file history backup system, you can not worry so much about working with a copy of your data. My data is continually backed up all the time, so I don't work with a backup as much anymore. I used to always sit down at the beginning of the day and I'd copy my project folder to a folder called Working, and I'd work all day on a copy of my data, and at the end of the day I'd copy it back. Depending on how your backup routine works or does not work, be cautious working on the only copy of your data. You can mess up data that you've spent hours and hours and hours on, so you want to be careful of that. Make sure to examine the result. GIS analysis doesn't always accomplish the desired results the first time through. It's an iterative process. You might need to change a tool, a criteria, the order of the processes. Maybe a 20-foot buffer on the road out here was completely wrong. I needed a 30-foot buffer. I need to change the criteria and rerun it. Maybe the clip tool wasn't what I wanted to use. I wanted to use the intersect tool. Those tools are real similar. They do really similar things, but you know, only by really critically looking at and analyzing your results can you determine if the tool did what you think. So take time to look real closely at things. All right. So did you get the results you expected? Did things perform correctly? Did it answer your question? Finally, presenting your results. Know that depending on your role, drawing conclusions may not be your responsibility. Either way, you're probably going to produce some kind of output so that your work can be shared, whether it's a map or a table or a graph. In the end, your analysis results may suggest that a particular action is needed, or it could raise new questions that prompt you to start the analysis all over again. All right, that's it for this one.